Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Okay. Hello, everyone. I am very happy to invite Professor Alberto Sá from Unicamp, Brazil, to deliver our colloquium at our center. Alberto has been Alberto, can you hear us?
Yes, now I can hear you, but before I was not
Oh,
here
before
anymore.
you could not?
No, I lost your introduction.
Oh, okay. Okay, let me introduce you again. Okay, hello everyone. So I am very happy to invite Alberto Sa, Professor Alberto Sa from Unicamp, Brazil, to deliver the IF Colloquium. Alberto has been a long-term collaborator of mine, and we are still collaborating. Alberto did his BSc and PhD from the University of Sao Paulo, and then did a postdoc from the University of Santiago de Compostela, Spain, after which he joined Unicamp, the State University of Campinas, as a faculty member. Apart from that, he has also been an associate member of the ICTP Trieste, Italy, and spent extended visiting periods at various universities around the world. And he has also been a regular visitor to Caltech in the US under the former US-Brazil Control and Dynamical System Alliance. So with this introduction, I would give the stage to Alberto.
Okay, thank you very much, Saikat. I need first to apologize because this seminar was to be 2 weeks ago, but I had some problems. I caught a very strange cold. Perhaps maybe it was COVID, I don't know. And I could not present the talk in the previous day 2 weeks ago. I will talk about this topic, Finslerian structure of black holes. This is a work in progress. I have two main collaborators, Hengame and Mauricio. Everything that I will talk, all the reference you can find in this paper, in the archive. If I did everything correctly, if you point your cell phone to this QR code, you should get the paper. I need to say that my works are kind of an application of some recent mathematical works by other people for black holes. So all the reference, the technical reference, you can find in this paper. A brief outline of my talk. You first will recall what is Finsler geometry. Is a topic that is not so standard. It's a standard topic in geometry, but physicists are not used to Finsler geometry. Then I will talk about the so-called Zermelo navigation problem. This is a classical optimization problem that's very important for us. In fact, I will spend the major part of the talk on this issue of Zermelo navigation problem, because if we understand this navigation problem, we will catch easily the ideas about causal structure of black holes. And then I will talk about these Painlevé-Gould-Strand coordinates for asymptotic, so for stationary spacetimes. That this is the starting point of the analysis of Finslerian structure for black holes. And I will present two examples, spherical symmetrical cases. In fact, it's only Schwarzschild that I will talk here. And then Kerr black holes, that of course is much more involved. So let's start with Finsler geometry. Look, everything started with this gentleman, here, Riemann, in his very famous habilitation dissertation of 1854, where he presented the basis of the modern differential geometry. In fact, in his work, he introduces the idea of infinitesimal arc length, and the most generic form for infinitesimal arc length that you can have in a manifold is this expression. Essentially, this is a notion of length on the tangent space of the manifold. So This will depend on the position of the manifold, this first set of coordinates, and on the components of the vector on the tangent space. These dx here are the components of the vector on the tangent space. This is the point of the manifold where this tangent space is tangent, and this is some kind of norm of this vector in this point. The work of Riemann was very generic. You have no restriction on this function f, more than very reasonable things like must be homogeneous and things like that. However, for some historical reasons, since the beginning, people realized that this restrictive form of f, we call this quadratic restriction, is very important because it's present in a lot of applications. So people start from the beginning to consider f only of this case, or of this form, and we start to call every geometry that has f of this form as Riemannian geometry. But in fact, the original work of Riemann has no quadratic restriction, okay? So in the beginning of the last century, this another gentleman, Paul Finsler, revisited the work of Riemann and started to investigate geometries without the quadratic restriction. So starting from the Finsler's work, people call Finslerian geometry all Riemannian geometry without the quadratic restriction. But it's a kind of funny because the original work of Riemann didn't have the quadratic restriction. This story is very well told in this paper by S.S. Chan, published not so much time ago. And the title of the work is quite clear. Finsler geometry is just Riemannian geometry without the quadratic restriction. Everything that you want to know about the interesting history of this issue, you can find in this paper. Okay, Finsler geometry has some applications in physics. It's not very common, but you have some applications. The first application that I know is the so-called Hunder's spacetime, that it will be very relevant for us here. This was presented in this paper in 1941 by Gunnar Anders. And the idea was to consider some kind of extension of general relativity where the metric or the interval has this form. We see that we have an extra term here that we don't have usually. In the usual general relativity, we have the quadratic restriction, okay? If you square here, you have only this part of the metric. And this is the metric tensor, okay? From a very rigorous mathematical point, this is not exactly a metric, this is a norm. This is called the Minkowski norm, but we will not pay attention to these mathematical details. We will call this metric, as renders call the metric. This is not a metric, but because metric is connected with inner products, and there is no inner product related to this metric, only to this part of the metric, okay? This render spacetime has some very curious behavior. For instance, this interval depends, in general, depends on the direction that you take to make the measurement, of course. So if you are in a certain point of the spacetime and you take one direction, and if you reverse this direction, you have a different interval. That's why renders call asymmetrical metric. But anyway, this is homogeneous for positive lambdas in this sense, that if you multiply this by a non-negative quantity, you have this identity. Of course, that we don't expect this kind of things for special directions. Special direction in space-time, you don't expect this kind of behavior, but for for the time direction, we know that there is no time reversibility in physics. So you have no arguments to neglect this kind of behavior for time directions. This is very well discussed in this recent paper, more recent, not so recent, by Bekenstein, where he describes the physical restraint that you need to have for this term in order to have a space-time that's compatible with observational data. But we don't need this now. We can go directly to Zermelo navigation problem because Zermelo navigation problem is the central part for our work. This is a classical optimal control problem proposed by this gentleman, Ernest Zermelo, in 1930. And the problem can be put as this. A non-relativistic particle moves with constant unit velocity v under the influence of a given time-independent drift, vector field W. We call this wind because Zermelo proposed the problem as a boat problem. You have a boat that's moving under the influence of a flow in the river or on the wind. And the idea is to find the minimum time trajectory between two fixed points A and B. Okay, so you have here, let us consider a flat two-dimensional space. You have this point and this point. You have a small boat that can move in any direction, but there is a constraint. It has constant speed, unit speed, and you have some drift. It can be a wind, it can be a flow, anything. And the idea is, what is the trajectory that minimizes time, starting here and ending here? Okay, let us try to have some intuition in this problem. Okay, if you don't have drift, so if without any kind of external drift, the boat starting at point A can take basically any direction. Can go in this direction, can go in this direction, can go in any direction. So if the boat starts in this point, after a given instant of time, the boat can be anywhere on this circumference. Okay, it's a unit circumference because the vector v is a unit vector with the center in the starting point of the boat. Okay. This circumference is a typical geometrical construction that has a name, is the indicatrix. This is important for us here. Okay, so the situation is the following. Without the drift, the boat can starting here after a certain interval of time, can be anywhere on this circumference. Okay. So if you ask, what is the minimal time trajectory starting here and finishing here? Oh, it's easy. Okay, it is a straight line. It's only to choose this vector for the velocity of the boat. And the boat will start here and end here with minimal time. Any other trajectory, you will spend more time. Okay, this is trivial. Now, let us suppose that we have some drift. Okay, so we have a vector here, a vector drift here, and the boat still can go in any direction with velocity v. So the boat can start its engine to go in this direction, but the effective movement will be the composition of this guy and this guy. So, in fact, the boat will go in this direction because the movement of the boat will be the composition of the velocity of the boat by its engine and the drift. Okay, so the boat can go in this direction, the boat can go in this direction, the boat can go in this direction, in this direction. So after a given instant of time, what we have is that the boat that starts here can be anywhere on this same circumference. It's a unit circumference, but now the center is displaced. The center is displaced exactly by the vector W, exactly by the drift. Okay? So the indicatrix here is still a circumference, but now it's eccentric. It's not on the center of, the center is not on the starting point, but is displaced by this vector W, okay? Now, what is the minimal time trajectory for the boat starting here and finishing here? It's easy. This, in the case of constant W, this is very easy. You take here the straight line and you choose the vector, velocity vector in this way in order to have the effective velocity along the straight line, and this will be the minimal time trajectory. Of course, that the very interesting thing appears when W is not constant. Constant, I mean that can depend spatially, is always time independent, but can depend spatially. So then we will have some other things. For a constant W, the minimum time trajectory are always straight line, okay? The basics of Finsler geometry approach for the Zermelo navigation problem is the following question. Can we formulate this problem geodesically? In fact, it's not exactly geodesics because we are looking for minimum time trajectory. So this is more related to Fermat principle. Fermat principle that say that in mechanics, not only mechanics, but also in optics, the real trajectories are trajectories that minimize time. But anyway, this is, you are minimizing a function also. Mathematically, this is a geodesic problem. So the question is it possible to formulate this Zermelo navigation problem for general W as a geodesic problem? And of course, that the answer is yes. The answer is yes, but there is three different, qualitatively different cases. The so-called weak drift, in the case that the wind velocity is smaller than the boat velocity. The strong drift, in the case that the wind is strong, I mean the wind velocity, the drift velocity is bigger than the boat velocity. And the frontier between the two, that's the critical drift, when the drift velocity is equal to the particle velocity, the boat velocity. Before we go into the details of this problem, let us try to get some intuition in each of these cases, because this intuition will be important for us to understand the final results on black holes. Let's start with the weak drift. Weak drift is the case that we consider when you have a situation like this one. Since the W velocity, the drift velocity, W vector, has magnitude smaller than the boat velocity, you have no blocked direction. I mean, if you start the boat starting here, it can go anywhere, even if you go against the wind, you can win the wind, and you can escape, of course, okay? So you have an indicatrix. The indicatrix is always a circumference of unitary radius, but the important point is that the starting point A is located in the interior of the indicatrix. So if you start here, you can go anywhere on the indicatrix after a given instant of time. So you have this situation, you have the indicatrix, and the starting point is inside the indicatrix. In this case, you can easily find the minimum time trajectory between these 2 points. We know is only to do this construction. We can also solve this problem. We can solve this problem for any point on the plane. We can find always a minimal time trajectory. So this is the case where for any 2 points on the plane, you can find a geodesic. It's not exactly a geodesic, is a minimal time trajectory, but mathematically, we can think about a geodesic, okay? Now we have the critical drift. The critical drift, the situation is different because it's this situation, okay? Since W has exactly the same magnitude of V, there is a situation when V is aligned exactly in the opposite direction of W, that the boat that starts here goes nowhere because the drift drag in this direction, the engine try to put in another direction, and the boat will finally end here. This is the case where the starting point is exactly on the indicatrix. So you have this situation. Starting here, you can go anywhere in the circumference. What is the difference in this case compared with the first one? You can find a geodesic between this point and this point. It's easy. You can find a geodesic between this point and this point, but there is no geodesic connection connecting this point and this point. There is no connection because the wind is strong enough to prevent the boat of coming back behind this line. We can see some jam of a horizon here, and this is actually a kind of horizon. The difference in the critical drift case is that the geodesic problem sometimes has no solution. This is a case, for instance, that there is no geodesic connection this point and this point. The strong drift case is an exacerbation of the previous case. So you have some very strong drift, and even if you try to move against the drift, you end somewhere here. So we have, again, the indicator is the circumference, but now the starting point is outside the indicatrix. We have this one. So we have this conic structure, and the geodesic problem has solution only if the point is inside the cone. So you can find geodesic between these 2 points, you can find a geodesic between these 2 points, but there is no geodesic connecting this point and this point, okay? When we formulate this geodesic problem, we are discussing, this discussion is on the tangent space of the manifold. So we can think here as infinitesimal movements, okay? When I say that we start here and end here, this is an infinitesimal direction on the tangent space. In order to have the true direction, the true movement on the manifold, you need to take the so-called exponential map. You need to transfer this information that you move in some direction in the tangent space to the manifold, okay? But in the tangent space, this is the idea, okay? In each point, you have some directions that you can move. Of course, that this is suggesting that if we have some geometrical description for this thing, it cannot be Riemannian. Because Riemannian, I mean that with the quadratic restriction, you could not make difference. You could not differentiate directions. All the directions are equivalent. So if you try, if you put this in some geometrical framework, and we'll do it now, this geometric framework cannot be Riemannian. Okay? So let's now talk about the connection between Zermelo navigation problem and Finsler geometry. This is the question that I put in the beginning. Okay, how to formulate the Zermelo navigation problem as a geodesic problem? We will consider here the things are a little bit more generic. So consider a non-relativistic particle. Non-relativistic here means that it's basically moving around. We are not considering time dilatation, things like that. Is the simplest movement that we can have. So consider a non-relativistic particle moves constantly unit speed in an n-dimensional Riemannian manifold, M with some Riemannian metric on the manifold, subject to a time-independent vector field drift W, such that the modulus of the norm of the vector is evaluated with respect to the metric of the manifold. Is the curved generalization of that two-dimensional problem of the boat. Okay, and the question is: can the trajectory that minimizes the transit time for a particle traveling between two distinct points of M be described by a geodesic of some positive definite metric on M? The answer is yes. The answer is yes, and it's not a surprise that this positive definite metric will be something strange. Will not be Riemannian, because we expect in this problem, because we know now that there is some qualitative difference between the weak, critical, and strong case, we will expect some directional dependence. And if you have directional dependence, the underlying geometry cannot be Riemannian. Okay? So let's start with the weak drift. Okay? So in this situation, exactly in this situation, this norm is smaller than 1. This is the weak case. What is the positive definite metric that gives us the minimal time trajectory as geodesic? Surprise, surprise, is the Randers metric. The Randers metric from the Randers space-time is the metric with this identification. This vector A is given by this expression. This one form B is given by this expression. And lambda is this thing. And in the case of the weak drift, the restriction is positive lambda. So this metric for positive lambda is the metric that gives the minimal time trajectory of the Zermelo problem as a geodesic of this, of this metric. Okay? This is not really new. This is something that is well known from some time ago. But the final rigorous result, mathematically rigorous result, is quite new. It has 15 years, something like this. But the idea that the Randers metric can describe this minimal time trajectory for the Zermelo navigation problem is not so new. Okay. Now we have some new results, new mathematical results by other authors. The case of critical drift. In the case of critical drift, we still can formulate the minimal time trajectory as geodesic, but the metric now is the so-called Kropina metric. It's this metric But this metric is not defined for any direction, only for the directions that belongs to a certain half space on the tangent space, given by this restriction. These restrictions mean that the directions must be positively aligned with the vector drift. We know this condition. This condition is actually this one, okay? You can find solutions only if the drift and the displacement are aligned. So the displacement is the vector v. Did you remember? So there is no solution if you try to come back here. Only if you try to move in the same direction of the vector drift. Okay? There is some useful comments here. The Corpina metric that was obtained by some other methods can be obtained, and this is very important for us, can be obtained in the limit of lambda goes to 0 of the Render's metric. If you take the Render's metric and take this limit, you have the Corpina metric, provided you assume this restriction. Okay, this is important. So, provided you assume this restriction, this limit of the Render's metric gives origin to the Corpina metric. Okay, this is the Corpina work is from 2000 something. It's quite recent from a mathematical point of view. The last case is the so-called strong drift case. In this case, also there is a metric. The metric is called Lorentz-Finsler metric. In fact, there is two metrics. Okay, this is some technical detail. We have two metrics, but both metrics are called Lorentz-Finsler metric. And they are defined in a conic region of the tangent space, where you must obey these two conditions. And this is, if you work a little bit, you will see that is exactly that condition that we derived from elementary considerations before. This is the case where this metrics only define. It means that the geodesic problem is only defined if the points are the interior of a cone. We know this condition. Another interesting comment here is that the Lorentz-Finsler metric, in fact, the minus version of the Lorentz-Finsler metric, is exactly the same if you consider negative lambda in the Render's metric. So you can say, provided you have this restriction on the tangent space. So you can say that everything is Render's metric plus some restrictions on the tangent space. In the case of the weak drift, there is no restriction. If there is no restriction, it means that you have always a geodesic connecting 2 points on the manifold. In the critical case, is also Render's metric, but with the half space restriction, with this restriction, it means that you have, if you start in here, you have the geodesic problems is well posed only if the other point is on the right of this tangent line. This is the critical drift. And the strong drift is also the Render's metric, but now the restriction is a little bit more stricter. You need to, if you start here, the other point must be inside a cone here. Okay. Okay. So let's now start to talk about the implication of these things in general relativity. the space-time that we are concerned here, that includes all black holes, are stationary spacetimes. Stationary spacetime, it means that you have, there is a system of coordinates where the metric does not depend on t, okay? But the spacetime is, you don't need to be static. I mean that the foliations of constant t are not special. The only restriction is that there is a system of coordinates where the metric does not depend on t. T is a killing vector, okay? If the space-time admits a coordinate of this type, we call this a Painlevé-Gulfstrand space-time, because this is the so-called Painlevé-Gulfstrand coordinate. Not every stationary space-time admits a formulation of this type, but if it admits, we call this Painlevé-Gulfstrand space-time, or more precisely, a space-time admitting a Painlevé-Gulfstrand metric, okay? If you take this, we will see that all static black holes are of this type. Static black holes are quite easy. And the Kerr black hole, all the Kerr family black hole is admit this kind of construction. You need to have some very strange black hole in order to don't have this kind of decomposition, okay? This is the decomposition. This is related to ADM decomposition and things like that, okay? If you start with this black hole and you consider null geodesics, and null geodesics are light path, okay? All the causal structure of the black holes are determined by the null geodesics. So the null geodesics is something very important to understand the causal structure of black holes. In fact, the null geodesics define the causal structure of black holes. If you take dx equals 0 here, and you solve for dt, okay, 0, this is a quadratic expression for dt, you solve for dt, you have an expression like this one. Guess which f we have here? We have the Randers metric, okay? This was not the original proposal of Randers. Randers, he was concerned with the old ideas of Kaluza-Klein theories, and the idea is, the original idea of Randers was to consider a 5-dimensional space-time and try to get a 4-dimensional space-time by some kind of dimensional reduction idea. Here's different. Here's everything four-dimensional. We have, I would say, I dare to say, physically relevant space-time, because it's 4-dimensional. Any other dimension, for me, is difficult to consider physically relevant, but okay, this is, I will not start a war here, but you can start with a 4-dimensional space-time, and you get an effective Finsler geometry for the null geodesics, only for the null geodesics, okay? And now you can look for, you can start to investigate the null geodesics using some kind of Fermat principle, because the null geodesics are the geodesics that minimize dt, minimize time. So this is exactly the problem of the Zermel navigation problem. It's exactly the same problem, okay? Since f is Randers metric, and we know that all 3 different cases, the weak, the critical, and the strong case, all these cases are Randers metrics with some extra conditions, we can derive here a geodesic formulation for any value of this vector, for any value. Okay, and we will see what we have. Let us consider first. Of course, that I need to call the attention for this term here. This term implies that the propagation of light in a certain space-time does depend on the direction. Okay? And this is true, because what is a horizon? A horizon is a certain region where you can go in one direction, but not in the other. But you cannot go in the other direction. So it's not strange that the propagation of light rays depends on the direction. This is in fact natural, because we know that for black holes this is the case. Okay, so again, the idea that you can describe these things by using a Finsler geometry is not really so surprise. It's something that you could expect on some general arguments. Okay, that's all, as I just said. The direction of the light propagation make difference. The light depends on the direction of propagation. The light path depends on the direction of propagation. Okay, good. Let us consider an example. Schwarzschild black hole. Okay, Schwarzschild black hole is the Finslerian coordinate was proposed in the beginning of the century, exactly in the Schwarzschild black hole. And the idea was to show that the singularity, the apparent singularity in R equal to M is not physical, because you can choose a coordinate system where the singularity is absent. Okay, and the form of the Finslerian form of the Schwarzschild black hole is quite simple. Is only this generic form, but you take H as the Euclidean metric. Okay, this is the Euclidean metric. So if you try, and the drift is this thing. Okay, this is a radial drift in falling. It's a infalling radial drift. So if you try to understand the Schwarzschild black hole as a Zermelo navigation problem, and there is a very interesting framework called the river model of black holes. River model from black hole, where you describe black holes in a situation where you have some background manifold and some drifts. You can find this work. I have this cited in my paper. It's a very interesting framework to visualize causal structure of black holes. In the case of Schwarzschild black holes, this metric is quite simple. You have this is the Euclidean metric, and this is the vector drift. So Schwarzschild black hole can be understood as a radial infalling drift on a flat three-dimensional space, not space-time, space. Okay. If you do the calculations, these calculations here, essentially, if you why it's not come back? I don't know what's happening. I will. Look, we need to determine the solution of the ds equals 0. So we need to solve this for dt, and you have this expression for the function f. The symmetries of the Schwarzschild black hole, we will consider only points along the x. We will consider Cartesian coordinates, and we will take points only along the x axis. Okay, so the expression for that function f is this one. Okay, where lambda is given by this one, by this expression here. So we can see that the weak drift region is the region where lambda is positive. This means the exterior region of the black hole. The strong drift case is the interior region of the black hole, and the critical region is exactly the horizon. Okay, it's easy to determine the indicatrix of this function f, of this metric. It's not a metric, it's a norm, it's a Minkowski norm. You can easily determine the indicatrix. The indicatrix is given by this. This we can easily recognize that it is a sphere of radius, unitary radius, and the center of the sphere is displaced in the x direction by this quantity. Okay? So we have three different, qualitative different cases here, and we can show in this diagram. We have here the event horizon. This is the exterior region. In the exterior region, this displacement of the center is smaller than 1, okay? Because this is the norm of this vector is 2m over r. This is in the exterior region, is smaller than 1. So what we have is the indicatrix with the starting point inside the indicatrix. We have this situation. If null geodesics start here, the null geodesics can go anywhere in any direction, because any direction is allowed for this null geodesics starting here. Okay. Then we have the case of the critical case. The critical case is where this is equal 1. In this case, that corresponds to geodesics that starts exactly on the horizon. We have that restriction that we already know of the half space. The geodesics that start here cannot go outside. Okay, if you start here, you can only go inside the black hole. In fact, there is some very special direction here that you go nowhere. You'll be always in the same point. This is the definition of a trapped surface. This is the idea. You have some directions here. If you have a laser here, there is a special direction that if you point the laser, the light will not move. Okay, this is definition of a trapped surface. And now you have the situation in the inner part, in the inside of the black hole, in the interior of the black hole, where this displacement is bigger than 1. So you have that the point is here, the indicatrix is here. I mean, the point is outside the indicatrix. So we have that conic region, okay? In this case, all geodesics starting here are dragged inside this cone, okay? This is something that we know in the interior region of the black hole. Here on the horizon, if you can try to escape against the gravitational pull, there is some very special direction where you are kind of stuck. Here is no. Any trajectory, any null geodesic, you'll be dragged towards the singularity. Okay. In the paper, we also discussed the case of Reisner-Nordström, but Reisner-Nordström is technically a little bit more difficult, and the situation is almost the same here. So I will not spend some time on Reisner-Nordström, but of course I need to talk about the Kerr black hole. The Kerr black hole, the situation is much more complicated. The biggest complication with Kerr black hole that in fact precludes the introduction of a river model for Kerr. You cannot understand the Kerr black hole with that picture where you have some flat space and some kind of flowing river, some drift. There is no interpretation. You need to use another ideas. But this is because it's a well-known mathematical result that the Kerr black hole does not admit Pine-Levé-Goldstrand coordinates with flat H. It's impossible, okay? But for our Finslerian approach, we don't need this restriction of H being Euclidean. So in fact, we can write the Kerr black hole in this form. This is the so-called Natário coordinates. We have this, the reference in the paper, where H now is this metric, is like everything with Kerr is a little bit complicated. The drifting is given by this expression and everything here. There is a drawback with Natário coordinate because we cannot solve this integral. So this is a kind of you have no explicit expression of this coordinate. It's only given implicitly. So, but it's enough for us. Okay. In particular, we can determine the indicatrix for the Kerr matrix. And the indicatrix is given by this expression. In the Kerr matrix, the construction is a little bit different. We need to take the equatorial plane because, okay, you don't need to take the equatorial plane. My examples that I will show here is in the equatorial plane. So once you have in the equatorial plane, you have axis symmetry. So you have no special direction in the equatorial plane. So we will take again every new geodesics starting along the x direction. Okay. We are reintroducing here the Cartesian coordinates. This theta, phi, and r. This is the so-called oblate coordinates. We can change back to Cartesian coordinates, and we write now the indicatrix on the Cartesian coordinates on the equatorial plane with the starting point around the x direction. Okay. The first thing that we realize here is that we don't have any more circumference spheres. We have ellipses. This is something that is quite easy to prove, that if H is not Euclidean, the indicatrix generically will be ellipses, okay? If the H is Euclidean, it's always spheres. But if H is not Euclidean, then the indicatrix will be ellipsoids, okay? If you take the restriction on the equatorial plane, you have ellipses. So you have ellipses with the center now are displaced by these two quantities. That's of course related to the radial and angular direction of the drift, okay? And now we have some more interesting situations. Because we have two, I will call local horizons, though two, in fact, they are killing horizons. We don't need to go into details here. That is the ergosphere and the horizon, okay? So the first situation is in the region outside the ergo surface. Ergo surface is the frontier of the ergosphere, okay? And is given by R equal to M in the case of the Kerr black hole. In the outside region, The situation is exactly the same of the weak drift case of the Zermelo problem. You have some indicatrix, and the starting point is inside the indicatrix. So if you start here, you can go anywhere, in any direction. So in the exterior region of a Kerr black hole, the situation for light rays is similar to the exterior region of the Schwarzschild black hole. Null geodesics starting here can go in any direction. Okay. In particular, it can go to infinite. Okay. If you go in this direction, you can going in the opposite direction of the attraction, you find and you reach the asymptotic infinite. Okay. The scry, because this is a time null like infinite. Okay. Then you have the ergosphere. The ergosphere is the ergo surface, that is the boundary of the ergosphere, is the critical case. In this case, the indicatrix is an ellipse, and the starting point is exactly on the indicatrix, and this is the tangent line of this point. And if the light start here, if the null geodesic start here, you can go any direction that is on the correct side of this plane. If you go in this side of the plane, I hope you can see my cursor here. In particular, you can escape the ergosphere. You can go, for instance, in a quasi-parallel direction to this straight line, and you can escape the ergosphere. You can start in the ergo surface, a null geodesic can escape to infinite. The ergo surface is not a horizon, it's not an event horizon, okay? Inside the ergo surface, what you have is that you start to have the indicatrix in such a way that the starting point is outside the indicatrix. So what you start to have is to have a conic region, okay? And the horizon, the event horizon, is the situation where the conic region is in such a way that it's impossible for a null geodesic starting here escape to infinite. Okay, we cannot see because the scale is not the best here, but this starting point is outside the ellipse. Okay, so we have here a conic region, and the conic region is aligned in such a way that it's impossible for a null geodesic that started here to escape to infinite. Not if the starting point were here, we could still escape to infinite, okay? But here, not. Inside the horizon, the situation is worse. This conic begin to collapse, and if you start here, you can go basically in the direction toward the center, okay? The interior region of the Kerr black hole is quite complicated. We know that we have an inner horizon, and we have in the center ring singularity. We discussed this in details in the paper. Frankly, it's impossible to represent in a simple diagram like this one. Okay. So it's time to make a summary. What we learned with this thing? I think that we learned two interesting points. First is that the task of finding null geodesics of any stationary spacetime admitting Pine-Levé-Goldstern coordinate is a Finsler geometry problem. Okay. Since null geodesic is connected to causal structure, we can rephrase this. The study of causal structure of any stationary space-time that admits a plane-level Gaussian coordinate is a Finsler geometry problem. Okay, you can try to relax this and try to do things for space-time that does not admit plane-level Gaussian. People try to do this, and in fact, there is some works. I would say that many works that precede our work that do these things, but only for the exterior region. The first, I would say, complete description, including exterior, horizon, and interior, is presented in your paper. And another thing that I like much is that this Finslerian description offers us an enhanced understanding of the causal structure of black holes, presenting the behavior of new geodesics on the ergo surface, horizon, and their interior region in a novel geometrical terms. I would say that we can reinterpret the river model of black holes in terms of the Finslerian description. Okay, for the Schwarzschild case, the situation is exactly the same, but for the Kerr is different, and I believe that our approach can offer a better understanding than the usual approach based on some local twists. Okay, I think that I finish here, and we have time to discussions, questions. Thank you very much for the attention, and thank you very much for the opportunity. And I apologize again for my failure 2 weeks ago.
Okay, thank you. Let's thank the speaker. Any question? Yeah.
Oh, okay. I would like to know, like I mean, what I perceive of the concept of Finsler geometry is that is it correct to think about in this way that the Finsler geometry is just the relative geometry respect to the Riemannian geometry, that the observer or maybe whatever move with the vector W?
This is the Randers case. Finsler geometry is not restricted to Randers, okay? The Randers metric, this is a particular case of a Finsler metric. I say that your proposal is okay, is perfect. It is a way of understanding these things, but there are another Finsler geometry that are not Randers, okay? So the Randers metric, that is particular Finsler metric that we consider, I think that your picture is correct. In fact, if you take that paper that I presented in the beginning in the American Mathematical Notices by S.S. Chern, I think that he says exactly this. The Randers case, you can think that it's a kind of, you see some geometry from a moving frame. This is the idea, okay? You are correct, but only for Randers, okay? For our purpose here, everything is Randers, okay? But not true for generic Finsler metrics, because there is others Finsler metrics that are not Randers.
Yeah, but if I perceive it that way, okay, and you say it will be correct in some extent, inconsistent to like in for GR in general, because you know that when we say the observer move in relative to some source or something, that but in Finsler geometry tend to use like the Galilean transformation. I don't know if I correct.
Look, I think that there is some confusion. Probably I was not clear. The underlying Finsler geometry of the causal structure problem has nothing to do with general relativity. You have the original problem, find the null geodesics. This is a general relativity problem. So you can solve this without any Finslerian conception. What I show is that there is another possibility of viewing this kind of problem in terms of effective Finslerian geometry. But this Finslerian geometry is not the real geometry of the space-time. This is discussed in the Bekenstein paper that I showed in the beginning. If you consider the Finsler metric as the real metric of space-time, there is a lot of restriction on that B function, because there is a lot of data, and you cannot alter if you take, for example, the Schwarzschild metric, you cannot alter the Schwarzschild metric without spoiling a lot of information that you have on the solar system data, okay? So the Finsler description is not real physical description, it's a kind of affective description. And of course, if it's an effective restriction, this is not fair to put a restriction like Lorentz invariance. If you think, if you require Lorentz invariance, B must be 0. It's not possible to have Lorentz invariance with B different from 0. Okay? In the original proposal of Randers, he escaped this thing because the original space-time was the unphysical 5-dimensional space-time. Okay.
Thank you.
Yeah.
So Alberto, do all the stationary spacetimes admit Penlev-Gustran coordinates?
I would say that all physically relevant, yes, but there is some very strange mathematical artifact that you have some problems. I don't remember exactly how the reference, but I can. But for all the physical relevant case, you can find a Penlev-Gustran coordinates. The problem is that there is more than one definition of Penlev-Gustran coordinate. There is the so-called strong, weak, and at least the weak form of the Penlev-Gustran coordinate is always available for any stationary spacetime. But sometimes you need the strong version. The difference between strong and weak has to do properties of that metric H.
Okay, and
there is a famous result in mathematical physics, and you find this result stated as the following statement: that Kerr geometry does not admit a Penlev-Gustran coordinate because they are thinking implicitly the strong form of Penlev-Gustran coordinates. These Natal coordinates that I show you is not a strong version of Penlev-Gustran coordinates.
Okay, and one more question would be that what new can you say with this picture that you would not say otherwise in the usual?
Nothing. This is only a new interpretation in geometrical terms.
Okay.
I don't expect to discover anything here that's not possible to discover in the usual approach. Okay. This is only a new way of visualizing, I would say, the causal structure. This is good because you can somehow make a unification of the real black hole with some analog modes of black holes. Because in analog mode of black holes, you have some unphysical metric that mimics somehow the usual space-time metrics. And if you use this Finslerian approach, you can unify both. This is But in fact, I need to confess that there is nothing new that you can learn in this approach that's not available in the other. In fact, I must say, basically for the students, that's quite difficult to find something new in black holes, okay? This is 8 years field of study, and things that are really new are not so easy to find. You can reinterpret things, but really new things, new facts, is quite difficult.
Okay, so if we do not have anything on the time. Okay, so let's just thank the speaker once more.
Thank you, guys. Thank you very much.
Okay, let's stop it here.
Okay. Bye. Perhaps next time I can go to Thailand. Bye.
Bye.
Theoretical physics.